Can you see my screen? Please let me know.
Yes, sir.
Yes, you can mute.
Sir.
Okay. So in the last class, I have started this band structure of open circuit PN junction, but I could not complete it for because of the lack of time. So I'll be again, because I could not stop the derivation in the middle, I'll start it from the very beginning. So we have open circuited PN junction. So the open circuited means I can say that overall current in the PN junction, the element called PN junction diode is 0. Because in open circuit the current is equal to 0, and in a short circuit the overall voltage is equal to 0. Now if you see the band energy band diagram, we have a constant Fermi energy level throughout the element. So whether it belongs to the P region or the N region, we have only one common Fermi energy level. And then from the things that we learned from the review of semiconductor physics, we know that in the
Not visible, sir.
what? Please repeat. Am I not audible or what? PPT is not
visible.
Okay, I'll just check. Now is it visible?
Yes, sir.
Okay, fine.
Sir.
Okay. So everyone please mute yourself. So in this diagram, we have already known that in a N region, in N type region, the Fermi energy level will be close to the conduction band. That's why we have written ECN very close to the EF. And also we also know that in the P type region, we have your Fermi energy level close to the valency band. Okay, so that's why we have taken the valency band energy level close to the EF on the P region side. So we cannot have a uniform energy bands, conduction band energy level in the P region and N region. Because in order to maintain the same EF, there should be two different conduction band energies and the valency band energy. So there's as if there's some kind of energy transition when we are moving from P region to N region. So you can observe that the conduction energy band, when we are moving from P region to N region, it is decreasing by an amount of E naught. This we are calling it as a energy gap, E naught. In open circuit condition, we are calling it as E naught. Okay. Similarly, by the same amount, the valency band energy level is also decreasing from P region to N region. And also, if you see the energy gap between the conduction band and the valency band, EG, we call it as a EG. The average value we are mentioning by a dotted line. That average value is also declining by an amount E naught. Okay, so there's some kind of a contact potential between the P side and N side across the junction, because of which we are seeing a decline in energy by a value E into V naught, where V naught is a contact potential, E naught is equal to E into V naught. So our journey is to derive the value of this E naught, from which we are going to derive this contact potential V naught. So if we once we got the E naught value, if we simply divide by the charge of electron, we'll get the contact potential V naught across the junction. So from the conduction band, from this conduction band or the valency band of the diagram, we can write that E naught as ECP minus ECN, because ECP is here, ECN is here. So if we in between you have this E naught, so E naught I can write it as a difference between ECP and ECN. Similarly, I can also write E naught as difference between EVP and EVN. Okay. And also I can write E naught as a summation of E1 and E2. So E1 and E2 are there is no physical significance for those numbers. Just in order to derive, we are using some intermediately variables E1 and E2. So this E1 is nothing but so if you take this E1, it is nothing but half EG minus EF. Okay. So we have written these values. So EF minus EVP is equal to half EG minus E1, and ECN minus EF is equal to half EG minus E2. So only we are just writing this equation just from this diagram. Okay. So EF minus EVP, the first equation is EF minus EVP is there. So let us check where is EF and EVP. So this is EF, this EVP. So we are talking about the this gap. EF minus EVP is this gap. So this gap is nothing but half EG. This is half EG minus E1. So if we remove E1 from this half EG, we will be remaining with this value. Okay. Similarly, if we go to the N side, ECN minus EF. This is ECN. This ECN minus EF. EF is this one. So we are talking about this difference, this area, this difference. This difference is nothing but half EG minus E2. Okay, so if we remove E2 minus, sorry, half EG minus E2, we'll get this ECN minus EF. So we're writing an equation for them. Okay, now if we add E1 and E2, so this is E1, this E2, then we are getting again E0. Okay, so we have equations E0 is equal to E1 plus E2. So keeping these equations aside, so we want to derive the value for E0. So I'll take the whiteboard now and derive at one place, and later on we can come back to the PPT and we'll let us check whether our equations are right or not. Please mute. Okay, is the whiteboard is shown on your screen? Please unmute and answer, or you can leave in the chat box. You can type in. Yes, right?
Yes, sir.
Okay, fine. So I'll begin with the equations. So from the diagram we have written EF minus EVP equal to half EG minus E1. We have this equation, and then we also have ఎవరమ్మా అక్కడ కంట్రోల్ చేస్తున్నారు, కొలాబరేట్ చేస్తే అలా చేస్తున్నారా? ఓకే, సో ఇఫ్ యూ వాంట్ టు డూ దట్ ఐ విల్ డిసేబుల్ దట్ ఆప్షన్. So I'll give you a chance for you to edit the whiteboard, okay, at a later point of time, not now. And then you have ECN minus EF equal to half EG minus E2. So let us call this as equation 1, this as equation 2 for time being. So if we add 1 plus 2, we'll get EF minus EVP plus ECN minus EF equal to half EG plus half EG is EG, energy gap, minus of E1 plus E2. We already know that E1 plus E2 is nothing but your E0. From this, I can write that E0 is equal to EG minus of EF minus EVP minus of ECN minus EF. This, let us call this as equation number 3. So till here, please note it down. I'll give you 2 minutes of time for you to note these equations. So because there is derivation, unless you do with your hand, you will not be able to comprehend anything. So as I told you earlier, I will be randomly asking some of you to showcase their notebook. Okay. So I hope everybody might be writing all these 3 questions. Now somebody is pointing out. So whiteboard is not visible, sir. Okay. Okay, I got to know from you. Okay. I hope it is now visible, or is it not visible yet? Otherwise, I'll go for my own board rather than depending upon the teams. Okay, no need to worry. At least is my screen visible now? So I hope whiteboard is visible. A white blank space might be visible now. I'll quickly write all the equations. Yes, right. So you can write along with me. EF minus EVP equal to E naught is equal to EG minus of EF minus EVP minus of ECN minus EF, which I'm calling it as. Still, it is not visible. I guess it is visible. Please let me know. Is it visible or not? Not visible. No? Now is it visible? So again I reshared it now. Please check and tell me. Now is it visible? Okay. So from this, what I will be doing is I'll be writing the expression for EG and the expression for this second term and for the third term. Okay, that's what we are going to do. First, we shall consider the equations for the electrons. So if you remember, the expression for the electron concentrations N is equal to Nc into exponential of minus of Ec minus Ef by kT. So this we are derived in the intrinsic semiconductor. Now same is valid even for the extrinsic semiconductor also. Only thing is that the number of electrons will be nearly equal to number of donor ions. Okay, because we are talking about the n type of material. Now instead of EC I will be writing ECN. Okay, now instead of for n type material I will be writing n with subscript n. Because it's a open circuited condition, I can even mention n and not. So not implies it's open circuit condition. Okay, so this is equal nearly equal to nd. So let this as equation A. Similarly, I have P equal to nv into exponential of minus of EF minus EV by KT in an intrinsic semiconductor. If I go for a p-type semiconductor, I will write it as PP naught equal to NV. Instead of this valence band, I will be writing EVP, and this value will be nearly equal to acceptor ion concentration, and I'll call it as equation B. Now from equation A and B, so if I rewrite this equation A, rewriting equation A, what I will be doing is I'll be taking this exponential term to the other side, and again I'll take logarithm on both sides, from which I will be getting ECN minus EF by KT equal to log n it will be log n NC by ND or ND by NC, which one you will get. Please try it on your own on one side. So I'll be getting NC by ND. Because of the minus sign, this will be interchanged. Instead of ND by NC, you will getting NC by ND. Now from which I can write ECN minus EF is equal to KT log n NC by ND. Okay, so this is the expression that we need to replace in the equation 3. Okay, so again, so I'll name it as equation 1, and again rewriting equation B, I'll be getting similarly EF minus EVP by KT equal to log n NV by NA, from which I will be getting EF minus EVP is equal to KT log n NV by NA. This I will call it as equation number 2. So everyone please note down till here, because I may move on to the next page. So all this equation might not be visible for you. So I'll give you 2 minutes of time so you can note it down. Okay. So in these equations, in the equation 3, we have 3 terms: EG, EF minus EVP, ECN minus EF, of which we already derived the expressions for ECN minus EF and EF minus EVP. So now we have to derive an expression for EG, which if we replace, we'll get the expression for E naught. Okay. So copy it down quickly. So have you finished copying? You can, if you have not yet finished, you can type in the chat box. I'll wait for a few more minutes if you require. Otherwise, I'll continue the derivation. Okay, I hope that everybody has copied the derivation. Okay, I'll wait one more minute and then I'll continue. Okay. So we have an expression for n and we have expression for p. If you remember from the review of semiconductor physics, you have something called mass action law. So mass action law says that n into p equal to n squared. So if you use the equations a and b in this expression, then it will turn into nc exponential of minus of ec minus ef by kt into nv to exponential of, I can write from a and b, ef minus ef minus ev by kt equal to n square. Now, so I'll write the exponential, I'll take the exponential terms at one go. So you have exponent of a into exponent of b, it will result in exponent of a plus b, right? So I'll be adding these terms. If I add within the minus sign, I'll be having ec minus ef plus ef minus eb. So this minus ef plus ef gets cancelled. You'll be left out with ec minus ev by kt equal to ni square. Okay. Now this ec minus ev is nothing but your energy gap eg. Okay. So I'll rewrite it as nc into nv exponential of minus eg by kt equal to ni square. From this, we'll get eg equal to kt log n nc nv by ni square. I'm simply taking these terms to right hand side, or where I just interchange the terms and taking the logarithm on both sides. Okay. So this is your equation number 3. Okay. Now replacing 1, 2, 3 in equation. So equation number 3, number 3, not Roman 3. Equation 3, we'll be getting E naught equal to kt log n nc by nv by ni square minus of kt log n, it's cf minus evp. Ef minus evp equal to kt log n nv by na minus kt log n, and again you have ecn minus ef. Ecn minus ef is kt log n nc by nd. Now I will be taking kt as common. and taking the logarithm is also common. You have log a minus log b, it is log a by b, right? So it's nc nv by ni square ni square. Here if this minus is term is there, right? So this numerator and denominator will get interchange because log a minus log b will become log a by b. So it will be na by nb. Similarly for the next term also it will be nd by nc. Now here nc gets cancelled, nv get cancelled. You'll be left with e naught equal to kt log n na nd by ni square. Okay, so this is what we were looking for. So let us call this equation 4. Okay, so from this I can calculate the contact potential V naught. So contact potential in open circuit condition V naught, or the barrier potential at open circuit condition V naught is equal to E naught by E equal to KT by E log n Na Nd by Ni square. Okay, now if you take this term kt by e, this term kt by e is known as volt equivalent of, just a minute, volt equivalent of temperature. It's written by a symbol V suffix as a V with a subscript T. Okay, so Vt equal to K into T by E, where K is your Boltzmann constant, E is charge of electron, T is your absolute temperature. Now if we take this K to the denominator, it becomes T by E by K. Okay, now if you take your calculator and you can take the terms for these are constant. Electron charge is constant 1.6 into 10 power minus 19. Your Boltzmann constant is also a number, a constant. So these values you can get from your Casio calculator. So in my calculator, E is given by the term constant 23. If I use constant 23, I'll get the term for E divided by constant 25. I am using constant 25 in my calculator for Boltzmann constant. Okay, if I do this E by K, I'll get the value around I'm getting in my calculator. I'm getting E by K is equal to 11,604. It is not exact. Okay, some depending upon your calculator it might be different, or depending upon the approximation you might be taking. So some might be taking 1.6 into 10 power minus 19. Some might be taking 1.602 into 10 power minus 19. Similarly for Boltzmann constant also, depending upon the precision to which you are taking, you will get different values. But obviously the value I'll consider it as nearly equal to T by 11,600. So in all the numerical problems, whenever you are encountering a term called Vt, you should represent Vt as T by 11,600. It's a volt equivalent of temperature. Vt is equal to T by 11,600. This you should remember, because he will not give the value. Instead he will be giving you the temperature value only. So he will mention the room temperature. So if he mentions room temperature, so it is 27 degrees. You should add 27 plus your 273. That makes 300 Kelvin. You should divide 300 Kelvin, 300 by 11,600. So if we do that, you'll be getting at room temperature, that is T equal to 300 Kelvin. You will get VT around, I'm getting actually I'm getting 25.86 something. So in your textbooks you will be shown that VT will be nearly equal to 26 millivolt. Okay, so at room temperature your volt equivalent of temperature is nearly equal to 26 millivolt. So in most of the objective questions you may have to remember these things instead of using your calculator again and again. So next thing we should do is from the equation 4 we have to rewrite, from equation 4 we will rewrite the expression. From 4 I will be writing V naught is equal to Vt log n Na Nd by Ni square. In this equation I already know that in n-type semiconductor I have in n-type semiconductor I have Pn is nearly equal to Ni square by Nd. So number of holes in a on the n side is equal to Ni square by Nd. Similarly I have number of electrons on p side is nearly equal to Ni square by Na. This we already derived in the previous classes. Okay, so what we'll be doing, we have to replace this Na, Nd and Ni squares such a way that we are writing the equation only in terms of this concentrations of holes or electrons. Okay, so what I will be doing is I'll be rewriting this expression. So instead of Na, Nd, so I can take Ni square by Nd square. For example, I will take this term. This is Nd by Ni square. So this I can write it as V naught equal to Vt log n Na by I'll write it as Pn, because it's at open circuit condition. I will write it as Pn naught. Okay, and know that the number of acceptor ions is nearly equal to Na is nearly equal to number of holes in the p-type semiconductor region. So Na is nearly equal to Pp naught. So naught implies that it's a open circuit condition. So I will rewrite this equation as V naught is equal to Vt log n Pp naught by Pn naught. Okay, this is our final equation that I'm going to use for the derivation of your diode current equation. This equation is often termed as Boltzmann's relationship. Okay, so this is at for a open circuit condition V naught. So when we are not providing any voltage to the PN junction, then this is the equation. You can write it till now, and if you have any doubts, you can raise your hand or you can drop it in the chat box. I'll just check. If you want me to scroll down or scroll up, please let me know. I'll do that if you want. Please note it down. I'll give you 3 minutes of time for you to write it. So one 12 marks answer question may be asked for you where you have to explain the energy band diagram. From the energy band diagram of open circuit PN junction diode, derive an expression for contact potential. Okay, this might be asked for one essay question. If you have any doubts, you can raise your hand, or you can type in the chat box. Because if I am letting you to unmute, some of you are talking, blabbering, in it's causing disturbance to others. Okay, so I'm not going to unmute you unless you specifically ask for it. Scroll down once. Okay, fine. At volt equivalent of temperature. Okay, so nothing. So Vt is equal to Kt by E is there, right? So we are rewriting that expression. So Kt by E, among this, your K Boltzmann's constant is a constant, your electron charge is a constant value. The only variable is your absolute temperature. So what I will be telling is your K by E is nothing but so if you take this units of K, so units of K is uh, I think it's in joules per electron or something, coulomb or something. Okay, so overall, if you write this expression, you will get an value in voltage. So I can say that the voltage value at a given temperature, say volt equivalent of temperature. That's what I'm saying. So what I'm doing is I'm taking down that K value to the denominator. So it becomes T by E by K. In the calculator, if you replace E and K values. So if I write 1.6 into 10 power minus 19 divided by K value. So K value, if you see in your calculator, I'm getting around 1.38 into 10 power minus 23 something. Okay. So if I do that E by K value, I'm getting a number near to 11,600. Okay. So at any given temperature, if you're going to find out the volt equivalent value, it will be in, you will be getting in volts. So at room temperature, I'm considering T as room temperature. I'm considering as T is equal to 27 degrees. So in case if nobody is mentioning that room temperature, you consider T equal to 27 degrees centigrade. So the absolute temperature is equal to 273 plus 27. Okay, scroll up. So in the last equation, what I have done nothing. So already you know from the mass equation, right? So I'll be doing that in this box. Okay. So already you have this n into p is equal to ni square, right? In n-type material, I'll be considering it as nn into pn equal to ni square. You know that electrons is numbers nearly is almost equal to your donor concentration. So n into pn is equal to ni square. So I will writing pn is equal to nearly equal to ni square by nd. So this expression only I have used it here. Okay. Similarly, if I rewrite for p-type material, I'll be getting np is equal to ni square by na. Okay. So in this expression, v naught is equal to vt log n na nd by ni square. I've taken ni square by nd as pn. So this will be 1 by Pn. Nd by Ni square will be equal to 1 by Pn. Okay, so I'm writing Vt log n Na by Pn. Okay, and also I know that acceptor ion concentration is nothing but your holes concentration in p-type material. So I'm writing Na is nearly equal to pp. I'm replacing that here, so I'll be getting V0 is equal to Vt log n pp by Pn. That O is only substituted O is to represent that it's a open circuit condition. Okay. At volt equivalent temperature, what happened to Na Nd by Ni square? No, no, no. It will be there. It will be there. I'm only just rewriting. It's as if we have a long expression Kt by E. Instead of Kt by E, I'm considering that expression as Vt. Still, you can see that in the final expression, you still have, besides the Vt, you still have your log n Na Nd by Ni square. I'm only representing this term. Where you still have this entire term V0 is equal to Kt by E log n Na Nd by Ni square. This term only I am representing with Vt. So it becomes Vt log n Na Nd by Ni square. You still have this logarithm term. Okay, it is not lost. I'm only representing, instead of writing three terms, I'm representing with a single term called Vt. Okay, I think I given ample amount of time for you. Okay, I'll move on to the remaining portions. Okay, if you require, I'll share this if possible. Export. I'll share this later. Okay, so I'll share this with you later. So do not worry. So I'll move on to this next topic. Okay. So in the last derivation, we got this expression V0 is equal to Vt log n Pp naught by Pa naught, which we are calling it as Boltzmann's relationship. From this, I can write Pp naught is equal to Pn naught into log n, sorry, not log, it is exponential of V0 by Vt. Okay, this set open circuit condition. Okay, so this is nothing but your barrier voltage. This is your barrier voltage or your contact potential. You can call this as at open circuit condition. If I write it for any other condition, so let us say that now we are giving a positive voltage. So you are giving a forward bias. In forward bias, what happens? You are going to give a voltage. See, in the last class, I have told you that whenever you're giving a forward bias, the barrier potential is going to decrease, right? So, however, when even though the barrier potential decreases, the changes you can observe only in the minority charge carriers. So, Uh, for example, I can say that if I add 2 to a large number, let us say 100. If I take a large number like 100, if I add 2, okay, the overall change is only 2%. Whereas if I add 2 to a small number, let us say 10, okay, then it is appreciable change. So 2 by 10 is around 20%, right? So that's the difference. So when you have a large number of majority carriers, the change in the number of carriers after a forward bias will also be will not be much changing. Of course, there will be small increase in the charge carriers. However, for our consideration, I can consider it as nearly constant. So this PP naught value will remain at PP naught even after giving a forward bias voltage of, let us say, V volts. So I'm giving a forward bias voltage of V volts. Even then, your PP naught will remain at PP naught. So nearly constant. Okay. Whereas your PN naught, so PN is nothing but number of holes on the N side. It's a minority carriers. So because when in the forward bias, the majority carriers are being injected into the holes on the P side are going to inject into the N side. The overall number of holes in the N side are going to be increased. So let us consider that increase as delta PN. So I will be writing it as PN naught plus delta PN. So this is the new number of holes in the N side. Okay. In the exponential term, earlier the barrier voltage was V naught. Now the barrier voltage will be equal to, the barrier voltage will be increased or decreased? Please respond. The barrier voltage will be increased or decreased, and forward bias voltage when you're giving a forward bias decrease, right? So instead of V naught, I will be writing it as V naught minus V. So the barrier voltage is now decreased by the potential that you are giving from the supply. I'm giving a potential of V volts. So your overall barrier voltage will be decreased by V units. So instead of the V naught, I'll be rewriting it as V naught minus V. So this is your Boltzmann relationship after you're giving a forward bias voltage of V volts. Okay. Now, what I will be doing is I have to get an expression for your carriers delta PN, how much your PN has changed. I want to get an expression delta PN because your current will depend upon the charge carriers. So I have to get this net change in your PN. So what I will be doing is I'll be replacing. So let us consider now in this expression, I'll consider this equation as 1, this as 2. Now I will replace 1 in 2 because the PP naught has not much changed. So it will be still be, so on the left hand side instead of PP naught I will be replacing PN naught into exponential of V naught by Vt equal to PN naught plus delta PN into exponential of V naught by minus V by Vt. Okay. Now I have to rewrite this exponential. Exponential has two terms, V naught by Vt and minus V by Vt. So what I will be doing is I will be writing Pn naught plus delta Pn into exponential of V naught by Vt into exponential of minus V by Vt. Now on the left hand side you have a term exponential of V naught by Vt. On the right hand side also you have a term exponential of V naught by Vt. These two terms will get cancelled. Okay. So if I take this term PN naught terms on one side, I'll be getting Pn naught into 1 minus exponential of minus V by Vt equal to delta Pn into exponential of minus V by Vt. Okay. Now if I bring this terms again to the right hand side, it will become this exponential term to the left hand side. If I will take, it will become delta Pn is equal to Pn naught into exponential of V by Vt into 1 minus exponential of minus V by Vt. So this becomes Pn naught into this exponential taking inside exponential of V by Vt minus this exponential V by Vt, exponential minus V by Vt will get cancelled. It becomes exponential of 0, that is 1. So I am getting delta Pn is equal to Pn naught into exponential of V by Vt minus 1. With this I will take it as equation number 3. Okay. So till here please copy. So I may extend the class by 5 or 10 minutes in order to complete this derivation. So please mind it in that. Screen not visible. Okay. Is it not visible for only tutorial or others also not able to see my screen? Please let me know. Okay, I'll be resharing that. It's visible. Okay, fine. Okay. For others it is visible. Anyways, I again reshared it. I think it is visible. So please note down this derivation. Only in this unit you will have this linear derivations from once this derivation is over, goes on smoothly. I think because the foundation has to be strong. I'm taking much time for the each and every derivation. Okay. So fortunately in our subject we do not get much of the integrations and derivations unlike your EMF subject. So EMF you need to work out more, whereas here mostly you will be getting only simple replacing one equation and another equation like that only. At max you'll be getting some exponential terms. That too only in the initial stage. With today's class I think almost derivations will come to an end. Okay. So I hope everyone has copied till here. So did you finish or anybody's left out? Please let me know. Okay. So I I'll move on to the next step. So if you check this equation 1, your PP naught is equal to PN naught into exponential of V naught by Vt, which is our original Boltzmann's relationship. So what I'll be doing is I'll be replacing this Pn naught value from equation 1. So I'll be writing Pn naught in terms of Pp naught, because Pp naught is a constant term, whereas Pn naught may or may not change, right? So instead of Pn naught from equation 1, I have Pn naught is equal to Pn naught equal to Pp naught into exponential of minus V naught by Vt. Okay, this I'm getting from equation 1. I'm just taking the Pn naught to the left. I'm leaving it on right hand side. I'm taking the exponential to the left hand side. So Pn naught is equal to Pp naught into exponential of minus V naught by Vt. And if I replace this, I'm getting delta Pn is equal to Pp naught into exponential of minus V naught by Vt into exponential of V by Vt minus 1. Okay, if you check this equation, so if you leave this term in the first expression, you have Pp naught. Pp naught is the number of holes on the p side, which is the majority charge carriers, which I told that they will remain nearly constant. And then you have in the exponential minus V naught. So V naught is a constant for a given material, your open circuit contact potential. And then you have Vt at a given temperature. If the temperature is constant, your Vt will be constant. For example, at room temperature, it is equal to 26 millivolt. Okay, similarly, it will be a constant at a given temperature. So this entire term is a constant term. Whereas in the second expression, you have V. So your voltage is changing, your exponential value will again change. So I can write that delta Pn is proportional to exponential of V by Vt minus 1. And now your entire whole current, IP, I suffix I with subscript P, IP is proportional to your change in holes in the N side. Okay, your overall change in the minority charge carriers on the N side. Okay, so I can write that IP is proportional to exponential of V by Vt minus 1. Okay, so if I take a proportionality constant, I will be writing IP is equal to ISP into exponential of V by Vt minus 1, where ISP is your proportionality constant. Okay, similarly, in the similar way, if you do it for the electrons moving from N side to P side, so electrons injected into the P side, I will get delta NP. So delta NP is the electrons that are injected from N side to P side will be proportional to exponential of again V by Vt minus 1. I'm not repeating the derivation again. Even in the examination, you can directly write similarly. Similarly, delta will be proportional to exponential of V by Vt minus 1. Now, electron current. So current due to the movement of electrons, In will be proportional to delta Np. And you can write In is equal to Isn into exponential of V by Vt minus 1. So your total current I is equal to whole current plus electron current. That's equal to ISP plus ISM into your exponential of V by Vt minus 1 is common to for both. This will be writing as I is equal to I naught into exponential of V by Vt minus 1. This we are calling it as diode current equation. Okay, in which the term I naught we are calling it as saturation current. Okay, your Vt is called as volt equivalent of temperature. Okay, so your current is exponential current. Your diode current is a exponential current. It's not a linear current. Okay, till here you please write down. So within 5 minutes I'll wind it up. Just is it visible? Is the screen visible? Scroll up. Okay. I think all the equations have adjusted, have zoomed out so that all the steps are visible. Still I have to scroll up. So I'll unmute first because it's the last few minutes. So you can unmute and ask if you have any doubts or regarding this whiteboard. If you want me to scroll up or scroll down, you can ask me. You can unmute and ask me. ఏంటమ్మా ఒకసారి మీ వాయిస్ కట్ అవుతుంది, మళ్ళీ చెప్పండి. Scroll up. Okay. Okay, is it okay now? This diode current derivation of the diode current equation also important. So you need not begin from the energy band diagram. You can directly start deriving this equation from the Boltzmann's relationship. Okay. If you want me to scroll down, you can tell me. Okay. So after this, we are left out with only two steps. So one is that we have to take the conditions for forward bias and reverse bias. So this is the forward bias condition where we are derived an expression for current I is equal to I naught into exponential of V by Vt minus 1. Now what we have to do is we have to check for some special conditions. Okay, what happens if the voltage given is a large number? It's a, you are giving a large voltage. Chat box. I think somebody is writing. Okay. So if forward voltage, if forward voltage V is large, then what happens? Your exponential of V by Vt minus V by Vt will be greater than 1. So I can conclude this expression within the bracket as I can rewrite this equation nearly equal to I into exponential of V by Vt. Okay. If the forward voltage is large, the exponential value will be much larger than your 1. So I'll be neglecting this 1. Okay. So this I will write it as IF, forward current. Usually your forward current will be large. Okay. Your forward current is limited by your circuit resistance. IF will be nearly equal to I naught into exponential by of V by Vt. Now in case instead of forward voltage, you have taken a reverse voltage. If you are taking a reverse voltage, now what happens? Instead of V, we have to write minus V. If voltage is minus VR, so let us consider that voltage as minus VR, then current I will take it as IR. IR equal to I naught into exponential of minus VR by Vt minus 1. If the magnitude of VR is large, if magnitude of VR is large, like earlier. Now, know that if x is a large number, e power x will be a very large number, whereas e power minus x will be very small number. Okay. So if modulus of VR is large, then exponential of minus VR by Vt will be small than less than 1. So now I will be neglecting this first term, exponential term. So I can write IR is nearly equal to I naught into minus 1, or I can simply write IR as minus I naught. Okay, which I am calling it as reverse saturation current. Okay. So forward current is usually an exponential curve, whereas your reverse current will be nearly a constant current. That too, this IR will be a very small value. It will be in microamperes or nanoamperes. Okay, it's a very small value. So your reverse saturation current will be, for germanium it will be in microamperes. For a silicon wafer, it will be in nanoamperes. That too, in the expression we have considered V by Vt, right? This is valid only for germanium. Okay, so in general, if you want to write the current expression, you'll write it as I is equal to I naught into exponential of V by eta into Vt. So in the denominator you have, instead of Vt you'll have eta into Vt minus 1. This is a general expression for any semiconductor diode. Whereas the expression I is equal to I naught into exponential of Vt minus V by Vt minus 1 is valid only for germanium. You have extra term eta. So eta is called as ideality factor. Okay, this eta value will be 1 for germanium, 2 for silicon. In the problems, if germanium is given, then you can directly use the formula. But in case silicon, if it has mentioned that it's a silicon diode, you should add a extra term called eta, whose value is equal to 2. Okay, you should keep this in mind. So ideality factor means that which is close to the ideal curve of a diode. So usually we are taking the germanium as reference. Actually, there is much more to tell, but it is out of scope for you. If I teach in detail, I have to go beyond that in the syllabus. So even I have to tell you more about the majority carriers, minority carriers, current components in detail. I could tell, but it is beyond your scope of the syllabus. Okay, so I have made the derivation as simple as possible. Okay, if you want to see for a enlarged derivation, including all the current components terms, we can uh, including your drift current and diffusion currents, all those things you can check it in your EDC textbook, Millman's Hawkins. Okay, so with this I'll end today. So you can simply write it down and you can leave. Sorry for extending for 15 more minutes, I think, but I have to end this today.